Okay, so turns out we need one more video to wrap up chapter 10. Just touching on a few conceptual things here. One is the idea of capillary action. So anytime you have a very small tube, and this could not just be like a glass or steel tube, but even like fibers in wood or paper, water is going to exhibit a tendency to invade that volume, to soak up, even if it means going against gravity. So this is essentially why paper towels are absorbent, because they're filled with lots of little tiny tubes in them or little void spaces that water wants to be attracted into because of its has to do with its surface tension. So it will get absorbed or sucked up into that. In building construction, that can be an issue. Capillary action can lead to water infiltration and mold growth, and so it's something that needs to be avoided. There are ways that you can prevent it from happening using proper construction methods and materials. So oftentimes, as engineers, we want fluid to flow. We want to cause it to flow, and one way we can do that is with a pump. Essentially, a pump is a way of artificially creating a pressure differential, which will cause the fluid to flow from the area of high pressure to low pressure. So one type of pump is a piston that compresses the fluid and forces it to flow. So here this intake valve opens up, fluid flows in, then it closes. The piston pushes down, the outlet valve opens up, and the fluid is pushed out around that into the outlet flow. This is a centrifugal pump. It uses an impeller to spin around and force the fluid to flow through the outlet here. And that really brings us finally to the end of the chapter. So the PowerPoint here that I've got posted on Blackboard contains several homework hints. Since I've got some time here in this video, I can go through it. So problem number 5, you're looking at the specific gravity of materials, but since the volumes are identical, you can essentially solve the problem just by comparing masses, or you can compare densities. You'll arrive at the same answer. For problem 13, pressure equals rho GH, just solve for H. You do always need to be aware of units, though. This problem is going to require some unit conversion between millimeters of mercury. So this is, like I said, mercury historically was used in manometers and barometers. So millimeters of mercury is a unit of pressure. We are going to want to deal with pascals or newtons per meter squared. So you're going to have to do some unit conversion there. For number 14, the weight of the vehicle is pressure times area. Just solve for the mass. Remember that weight is equal to mg. 24 is a lot like the Archimedes crown problem I did in the video. Problem 31, the submerged part of the iceberg will have a mass equal to that of the seawater it displaces. So again, that's buoyancy. The buoyancy force is equal to the mass of the fluid times gravity. The number 46. So this one is about filling an aquarium in a certain amount of time. So let's assume that we need to fill the entire volume of the aquarium in 4 hours. I think the problem is actually a filter. We're going to take the water out, filter it, put it back in, but it makes the same sense mathematically if we just think of it as filling the tank. So the velocity of a fluid flowing through a pipe is equal to the volume divided by A delta T, and our T here is 4 hours. So you should be able to solve for time. No, not time. Volume, I think. At any rate, problem 49. The weight of the roof. Oh, so this problem 49 is if you've got a building and air flows across the top of it, just like an airplane wing, the fast flowing air going across the top causes a negative pressure or uplift. So we want to know what kind of pressure would it take to lift the roof off of the building. Okay, so use Bernoulli's equation to find the pressure, and then pressure times area, if we're looking at a flat rectangular roof. Pressure times area is equal to force. We want to know the force required that would be equal to the weight of the roof in order to lift it. 58 involves viscosity. So remember this Greek letter here represents viscosity. That's actually what we're solving for in this equation. The equation for viscosity force equals viscosity times area times velocity divided by L. 61 uses PHYS equation for flow rate. Q equals, you'll have to look that up. I don't have it memorized, but that was in the PowerPoint earlier. And, it says 70. Skip this problem or try it for extra credit. Yeah, I'll just leave it for extra credit. So give that a try. All right, that does it for Chapter 10.